Okay, so welcome to this talk. This is the outline. We're having an introduction. Then we'll talk about a few patterns and anti-patterns in protocol design. So serialization formats, versioning, keys and subkeys in network protocols. And then we're going to talk about protocol specifications, and then there's a conclusion. So this talk might be a bit different than the others. Most talks here, the tech talks, are about finding bugs or dealing with bugs. And this is more about avoiding bugs when designing a system. So this is the first part in the slide that Marcel showed, where it's about designing secure systems. So maybe it's going to be a takeaway, especially for the developers among you. Maybe about Threema. What's Threema? Threema, the name stands for end-to-end encrypted messaging application. This was like the code name when the project was started. Then it was abbreviated to EEEMA. And because that sounds very technical, it was changed to Threema to include the 3 E's. So that's the name. It's not a real name. It was made up, but that's our application. So it's a chat application. You can use it to send encrypted messages. It's focused on security and privacy. It's developed and hosted in Switzerland on our own servers. And it's a paid app because we sell software and not data. And the clients are open source since 2020. The first version was released in 2012. This is what the website looked like. And maybe as a recap, in 2012, what was the world like? WhatsApp was not yet owned by Facebook. It wasn't end-to-end encrypted, so if you were in the same network, you could read the messages. People were still using Windows Live Messenger, if you remember that. People chatted over Facebook without TLS because by default Facebook didn't use HTTPS. So if some of you might remember Firesheep, you could sit in Starbucks and just connect to other people's Facebook accounts. Signal was still called Text Secure, and it was owned by Twitter. And it was essentially an SMS encryption app with no group support, no call support, etc. So the world was quite different back then. And in the last 12 years, a lot has changed, and messengers have become much more important, and there are much higher expectations what they should deliver. So let's talk about protocols. Threema has a different architecture than most server-backed applications. So our protocols are designed to create as little metadata as possible. And that means that many applications nowadays, they have the data on the server. So the server is connected to a database where, like, if it's a chat application, you have the groups, the chats, the messages. In our case, everything is on the client where possible. So the server is essentially just a dumb relay, and it sends along messages between the clients. And the way that clients talk to each other, that's the protocols. So that means that Threema works a bit differently than most tech companies. Usually you have a front-end team and a back-end API team. In our case, we have platform teams and a protocol team. But what's a protocol? So let's take a look at an example. I'm a paragliding pilot. It's a very interesting hobby. And often you fly quite lonely into some remote valleys in the Alps, but sometimes you're not alone in the air. And there are a lot of people there at the same time. So this is a photo from a paragliding competition where you maybe have 200 people in the air at the same time in the same location. And the question is, how do you avoid that people collide in the air? Because everybody makes their own decisions. These are all individuals. There's no air traffic controller like with motor aviation. So the way this is solved is by using a protocol. So there's a collision avoidance protocol, which basically says if two people fly towards each other, both fly towards the right, and then they don't collide. And if one of the two pilots has like an obstacle on the right side, like a rock wall, then that person cannot go to the right. So if that person has right of way, and the other person needs to go to the left from that person's view. So if everybody sticks to these rules, we're good. So that's a small example of a protocol that works quite well in practice. So on high level, protocol defines the rules for interaction between different actors. And on the network protocol level, a network protocol ties together aspects like message formats, versioning mechanisms, encryption logic, maybe error handling, and sometimes even flows that affect user interaction. So we learned a few things along the way in the last 10 years. So let's dive in. Let's talk about patterns, anti-patterns, with 3 examples. So these examples are 3 examples that we picked. They're not necessarily connected, but they all belong into this protocol design topic. First one is serialization formats. So maybe let's take a look at where Threema is coming from. So for Threema, the most important part that affects serialization is the messages exchanged between the different clients. And the question is, how did this protocol evolve, or this serialization format evolve over the years? So in 2012, we had the first version, which was the custom binary format, quite a classical one, which is like type length value encoded format. There was a rough specification in a wiki, and there were independent parser implementations in every app. And if you take a look at the advantages, this is quite simple and it's space efficient because there are small messages. That was the goal. But the disadvantage is it's not extensible, and unless you design it to be extensible, and there's no easy code generation possible. Fun fact, we did write like a description language for our protocol and a code generator, but usually you don't have that and you need to write it yourself. So let's take a look at a case study. So this is a text message in Threema, and it's as simple as it can get. It's just UTF-8 encoded bytes containing the message text. So it's simple and adequate, right? But what if you wanted to quote another message? Then where do you put this information? And as you might know, we do support quotes. So we use the workaround, which is called in-band signaling. So essentially you put the logic in the message itself. So if you have an old client that doesn't support quotes, you would actually see this message format. But newer clients, they parse the message and they extract the quote and they link it to the original message. So this isn't ideal because like you start mixing content and protocol logic, but at the time it was probably a good idea because if we would have done it differently, we would have needed to introduce a new text message. And that would mean incompatibility with old clients. So at that time, it might have been a good idea. Nowadays, we would have been happier if there would be extensibility. Another example is group setup messages. So when you create a new group, why are there so many status messages? So you can see these 3 groups. So let's take a look at the group setup message. This is the protocol message that creates a new group. So you have the group ID in there. And then you have a list of members, and every member is a Threema ID, so it's 8 bytes. So it's 8 bytes group ID, then maybe 8 or 16 or 32 bytes containing group member IDs. But what if we wanted to add a name to the group? This message isn't extensible because it's group members until the end of the message. You don't have an option to add something at the end because the parser expects Threema identities. So the solution was to send a separate group name message. But how do you set a group profile picture? The solution was send a separate group profile picture message. So now that you know this makes sense, right? Because first the group setup message comes in, the group is created containing the members, then a group name message arrives, and then a group profile picture message arrives. And of course, the clients could try to merge these status messages, but it's quite tricky in practice. Especially with the UI updates. So far we didn't do that. And you can see lack of extensibility in the protocol has an impact on the UX. So we thought, what can we do to solve this? And then we thought, well, to fix extensibility, let's just use JSON because it's a widely used format. And we started putting JSON in binary messages. The specification was still in a wiki. And the advantage is that now all of a sudden it's extensible because you can just add new keys to a JSON message and it can still be parsed. It's self-describing, usually, and it's a well-known standard format and you have many parsers available. But the disadvantage is it's space inefficient because you include the keys in every message. The fields cannot be easily renamed because then the old parsers break. You cannot easily include binary content. Of course, you can do base 64, but it's quite inefficient. And validation logic still needs to be written by hand. And there's things like JSON schema, which also includes validation, but JSON schema is, I don't know, at the draft 100 or something like that. It's still not finished, and the implementations, they vary. Some support certain validations, others don't. So it's not really a good solution. Also, let's take a look at a case study, the media message. That's one of these messages that contains JSON in the message body. So here you can see a few fields. So you have the caption, the file name, and the file size. And the caption field is called D. That's because it was originally called description, and later we renamed it to caption. But the field is still called D, so this is quite confusing. And then essentially you lose the advantage of self-descriptiveness, because you can take a look at the message and you have no idea what the letters mean unless you look at the documentation. So this is something that just how JSON works. And then in 2021 we took a look at new serialization formats, and we picked protocol buffers. And this is an efficient binary serialization format, and it's schema-driven and strongly typed. That means that if you have a message that you want to encrypt, you need the data and you need the schema. And using the schema, you can encrypt it, or not encrypt it, encode it to bytes. And to decode it, you need the schema again. The advantages are it's extensible, it's forward compatible, and if you take care, it's also backwards compatible. It's space efficient because it's quite compact, and you have rich type support, for example, numeric types, union types. You can rename fields at any time without an impact on the wire format, because internally it uses IDs, so numeric IDs. And the field number 3, it can be called caption or description, doesn't matter. The schema files can be managed in version control, and you can share them across projects. So the front end and the back end, like not the server, but the different clients, they can share the same schema files. And it's a well-established format. Now I'm getting a spam call, apparently. The schema files can be managed in version control, and it's a well-established format, so you have good libraries available for generating code. You do need to pick your libraries, because some of the libraries are less good, especially those from Google, but there are some very good libraries available. So disadvantages, it's not self-describing, and it's hard to debug on the wire if you don't have specialized tooling. Also, the inheritance isn't really supported, and if you do composition, you can have deep nesting because you have a message in a message in a message, and with code generation, that can be quite repetitive. But in the end, the advantages by far outweigh the disadvantages, and we started using protocol buffers for essentially all the network protocols that we design since 2021. And it's also quite useful to serialize data that you store on disk for configs, for example. Yeah, so let's take a look at versioning. The takeaway here is version all your protocols, because you will want to make some backwards incompatible changes at some point in time, even if you don't know it yet. And sometimes you can just include a version number of the protocol, like in the first message that's exchanged. That can be sufficient, but in some cases you might need version negotiation. And you really need to think about the transition phase. So if you introduce a mechanism for including the version, but then you have a partial rollout of new clients that use the new version, but you still have old clients around and you have mixed versions, you need to think this through to know what's going to happen. So this is an example protocol that we actually use in practice. So in this case, we have a client which is up to date and a server which is up to date. And you can see the server supports version 2 and 3, and the client supports protocol version 3. And the way it works is the client connects, then the server sends the server hello message, which includes the version, like the highest version that it supports, which is 3. The client responds with version 3 because it supports that as well. And then everybody's happy and the version is 3. If the client is old but still supported, for example here the server supports versions 2 and 3 and the client 1 and 2, server sends version 3, the client responds with version 2, which is the highest version that the client supports, and then the server accepts that and uses version 2 to communicate. But if the client is too old and only supports version 1, then it responds with version 1 because that's the highest version it supports, and then the server just disconnects with an error message. And this is also the part where you actually need to think about the transition phase, because if you have a client which you programmed 6 years ago, you will want that client to show a good error message saying that people should upgrade, and it should show how the client should be updated. And if you forgot to do that 6 years ago, there's nothing you can do now. And the last example is if the client is from the future, or maybe you work on like the new development version, which already supports the new protocol versions, but the server is outdated and not up to date. Then the server sends the server hello version 3, but it's too old for the client, so the client just disconnects. So this is a simple example of a version negotiation protocol that you can apply to your protocols as well. And so far we did one upgrade and it has worked quite well. So let's take a look at the third part, which is keys and subkeys in network protocols. And this goes a bit into the cryptography aspect, but we're not going to go too deep into it. So in many protocols, we have keys. For example, you have keys to encrypt messages. You might have keys to sign something. You might have keys to authenticate. So if you have a private key and a public key, by signing or encrypting something with your private key, you can prove that you own the private key, and someone with a public key can verify that you actually own the private key. So you have a lot of keys involved. And some things that we learned is only use a cryptographic key for one thing. Don't use it for different protocols, different encryption mechanisms. Because you could say, well, you have these 32 random bytes, let's just use it for everything. But in cryptography, don't do that. And one way to avoid it is if you need to use a key in multiple different scenarios, then use it as a root key. And use a key derivation function like Blake, for example, to derive different subkeys. And it's important that if you do that, if you have a root key and subkeys, only use the root key to derive subkeys. Don't encrypt something with your root key, because again, that can have unintended consequences. And if you write custom communication protocols, then use different keys per direction, because first of all, it's less probable that you accidentally reuse a nonce. And also, message confusion is much less likely. Message confusion is if, like, the recipient sends back the message to you, but switches around the sender and recipient on the metadata, and then you think it's a message from the other person, but it's actually from you. So this can be avoided by using different keys per direction. So, let's take a look at the next part. Specifying protocols. So it's important that you write down the protocols that you use, especially if you have different teams. And there are different ways how to do that. So how we used to work is we had the specification that described the message format, very technical, often no logic or flows. And this works nicely. If the company consists of 4 people that talk to each other and sit in the same room, this is perfectly adequate. But if the company grows, it gets more difficult and you have implementations that diverge in important aspects. And then you lose time to fix these divergences. So here's an example. This is the delivery receipt. It's the control message that is sent back. If I send you a message, then your client will receive it and will send back a delivery receipt saying that the message was received, so that my client shows the icon saying that the message was received, was delivered. And if the other person reads the message, unless this feature is deactivated, then I get a red delivery receipt. So this is the specification. It describes the message format, so different status codes. But how should it be displayed in the UI? And what happens if I receive a delivery receipt containing the type received, and then read, and then I receive received again? Should it go back to received, the status icon? Should it remain at read? Should there be an error? We don't know because the specification doesn't say. And developers are going to take assumptions and implement something, and they might implement it differently. So we thought, let's do better specifications, and what we tried next is RFC style specifications. So this is an RFC. It's declarative, so you say what the protocol should do, what the state should be, and it's independent from the implementation, which is on purpose because RFCs, they try to be implementation independent on purpose. But it means that it's easy to write, but it's hard to write well. And again, it's independent of the implementation. But the negative part is the logic and the flows cannot be described well. You need to have like a prose article and you need to read through the entire paragraphs. It's hard to implement because you need to translate the long paragraphs into code. Edge cases are often unspecified or underspecified, and when implementing, usually many questions arise. So we also had the experience that we wrote the protocol, we reviewed it, we thought it's good, and then we started implementing it, and then we realized that there are many edge cases that aren't described. And it seems to work well for ITF, but for us it didn't work very well. So we switched to the concept of steps. And the concept of steps is something that is used, for example, by web standards like the W3C, and it's like abstract algorithm, essentially. And let's take a look at different parts. So this is just an example, which handles what the client should do if the user updates a conversation and, for example, sets the notification settings to a different setting. So here we have a variable assignment. Let change be one of the following changes. So we can assign variables and then later refer to them. We also have conditionals. So step 3 is only executed if multi-device is active. So this is all the multi-device logic. Next one is we have error handling as well. So if the group does not exist, log a warning and abort these steps. So as you can see, this is very close to the code, to the implementation. And if it's close to an implementation, it means that implementations are going to be simpler because the specification already has the implementation in mind. You have less potential for mistakes because you need to go through these steps and you can find problems in the steps. And you can detect edge cases during the specification and avoid them, for example, by saying, if this happens, just return. And then you can avoid the entire edge case later in the protocol logic. Negative part is it's hard to write, and it's not easy to find the correct level of abstraction, because sometimes you don't know if you should go into the detail of what this actually means. But so far it has worked quite well for us, and we're still trying to find out how to improve these specifications. But of course, it's a lot of work. So how we work is we have version-controlled protocols. It's a combination of steps and protocol definitions like protobuf. You can changes can be discussed and reviewed in a merge request in version control. And you can tag protocol versions, and then projects can pull in the protocol versions files, and you can make sure that they are in sync. And it's not a solution that works for everybody. You need to find a solution that works for you, but this is something that has worked well for us. So to the conclusion, the key learnings for specifications is you want extensibility. Quality and precision in design is important, and good designs often takes many hours of work. And the best designs often have very simple but precise implementation logic. And you should also keep in mind upcoming potential extensions to design the protocols that you can add these extensions later on, even if you don't implement them yet. Deploying is easy and transitioning is hard. So certain aspects in our apps are hard to change because of earlier decisions, and that doesn't mean that these decisions were wrong at that time, but they have an impact on later. Also, always derive a subkey if you use keys, and if you do an implementation, precise pseudocode-like specifications, they prevent divergences in implementations. And if you do thinking in code during the design phase, then it's going to be much easier to implement them. And also, if you have one shared implementation, this pays off when your protocol grows. And maybe about this last part, as an outlook, we have started an internal project, which essentially does exactly that, a shared implementation that can be shared across different projects. And we don't know yet if this will solve all our problems. And the question is also, if we have this, do we even need a precise specification, or can we say the code is the specification? We don't know yet, but time will tell. So that's it from my side. Now we have time for questions.